derivative is the rate of change of one quantity in terms of the other quantity, and others call it the first slope of the function. We can apply derivatives in many aspects of our lives: business, speed, science, engineering, mathematics, economics, traffic control, volume and perimeter, and others. That is why it is important for us to know derivative. As I say earlier, we could apply it to different aspects of our lives. We would compute for the speed of a falling object, a rate of change of an arc, or how much speed are you traveling from a distance, and there are too much application of derivative in our lives. We cannot enumerate them all. That is why it is important for us to study calculus, especially derivatives. You must have know physics, trigonometry, plane geometry, solid geometry, business math, algebra, and linear algebra, because as I said earlier, there is a wide variety of jobs and researches wherein we could harness derivatives. It could help you solve derivative problems with ease if you have learned those core subjects of calculus.
So, this is my question related to volume. At a sand and gravel plant, sand is falling off a conveyor and onto a conical pile at a rate of 10 cubic feet per minute. The diameter of the base of the cone is approximately 3 times the altitude. At what rate is the height of the pile changing when the pile is 15 feet high? So, I browsed the internet and I arrived with an illustration like this. As you can see, this is the conical pile of sand, this is the conveyor, and the sand is falling off onto the conical pile. For this problem, we need to get all of the given. The given is the derivative of the volume with respect to time, which is equal to 10 cubic feet per minute. The derivative of the height with respect to time and the derivative of the volume with respect to height is still unknown. So what we need to have is, at what rate is the height of the pile changing when the pile is 15 feet high? So, as we know, we are looking for the height. So, we need to look for the derivative of the height with respect to time when the pile is already 15 feet high. And it is also stated on the problem that a diameter is equal to 3 times the height. So, we have this formula. The derivative of the volume with respect to time is equal to the derivative of volume with respect to height times the derivative of height with respect to time. So, okay, we know that the diameter is equal to 3 times the height. And we also know that twice a radius is equal to a diameter. And we also know a volume of a cone is equal to 1/3 pi r squared h. So we need to have a radius on this equation for us to substitute it on the formula. So twice the radius is equal to 3 times the height. So we arrive at this equation, which is radius is equal to 3 halves the height. So as we substitute 3 halves the height onto this formula, we arrive at a volume of cone 1/3 pi 3 halves height squared times the height. And as we distribute the square on the inside of this parenthesis, we arrive at a 1/3 pi 9/4 height squared times the height. And as we simplify this formula, we get 3/4 pi height cube. And the volume of the cone is not yet the derivative of the volume with respect to height. So we need to get it. So the derivative of the volume, which is the formula, with respect to height. So, as we apply power rule on this equation, we would arrive at the derivative of the volume with respect to height is equal to 9/4 pi height squared. So, we already have the derivative of the volume with respect to height, which is 9/4 pi height squared. So, we just need to substitute 9/4 pi height squared onto this formula. So, earlier we had the formula dv over dt is equal to dv over dh times dh over dt. So, we just have to substitute all the given onto this formula. So, dv over dt is equal to 10 cubic feet per minute equals dv over dh, which is 9/4 pi height squared times dh over dt. So, as you can see, I highlighted the height because we already know that the height is 15 feet already. So I just substituted 15 feet onto the height. So 10 cubic feet per minute is equal to 9 fourths pi 15 feet squared times dH over dt. So we need to isolate the equation here onto the other side for us to have an equation for the derivative of the height with respect to time. So I multiplied both sides by 4 for us to eliminate the denominator 4 on the right side. So we arrive at this equation. 4 times 10 cubic feet per minute is equal to 9 pi. I just distributed the square inside the parenthesis. So we arrive at 225 feet squared times the derivative of the height with respect to time. So I need to divide both sides 9 pi 225 feet squared for me to eliminate 9 pi 225 feet squared onto the right side. So we have an equation for the derivative of the height with respect to time. So 40 feet cubic feet per minute over 9 pi 225 feet squared. So we have the derivative of the height with respect to time, which is 40 cubic feet per minute over 9 pi 225 feet square. So as you can see, the feet or the square feet onto the denominator will be eliminated by the cubic feet onto the numerator. So we would only arrive at 1 feet. So as you enter this equation onto your calculators, you would arrive at this answer. dH over dt is equal to 6.29 times 10 raised to negative 3 feet per minute, or 0.00629 feet per minute. So we already have an answer at the question, what rate is the height of the pile changing when the pile is 15 feet high? So what does it mean? So it means that the rate of the height of the sand pile as the sand falls off a conveyor is 0.00629 feet per minute when it reaches a height of 15 feet. So we already solved the problem. See you at my next tutorial.